All right, guys. Hello, how we doing? Hope you all have been enjoying your snow days. So this lecture here, guys, is going to be the posted lecture for what would have been Wednesday's class, right? So I've been talking about how Wednesday was going to be taking the time to talk about everything about Chapter 8. Again, this is a one and done chapter, right? It's just one, notes day specifically for Chapter 8 here. It's one and done. That's it. It's about something called stoichiometry. Um, Now, stoichiometry, I know it's a funky name, but stoichiometry is the study of quantitative relationships between an amount of reactants and an amount of products. So it's really just looking at back at chemical equations like we did back in chapter 7 and doing some comparisons between some of the reactants and some of the products and mixing in this mole stuff that we've been learning about, right? So we've been spending a lot of time in chapter 6 talking about moles, and we're going to kind of mix between what we did in chapter 7 and what we did in chapter 8 talking about stoichiometry here, right? It's based on something called the law of conservation of mass and things being stoichiometry equal to. Utilize this sign here. I wouldn't really worry too much about these two uh, particular bullet points here, right? I would more so really just pay attention to this vocabulary word here, right, of stoichiometry and its definition right there, okay? Now, we've got something here called the mole map, and this is a really, really important visual sort of map here to help you figure things out, right? So a lot of the information on this mole map is actually not new information. It's all information we kind of covered in this previous chapter, chapter 6 here. Um, Again, we've been talking extensively about the mole, right? We've been talking extensively about the mole here. And every single time that we want to talk about the mole, we're always talking about not just the mole, but how to convert between moles and particles, moles and grams, for example, or moles and volume. In order to do that, we had to use some specific numbers in order to do that, right? So, for example, the first thing we learned about last chapter was how to convert between moles and some amount of atoms or some amount of molecules, right? And in order to do that, in order to convert between moles and particles or moles and atoms, whatever, we had to use that really, really annoying long special number, 6.02 times 10 to the 23rd. And then we always had that either one mole divided by 6.02 or 6.02 divided by 1 mole. And that's kind of the conversion factors we used in order to do that, right? Then the next thing we talked about was how to convert between moles and some amount of grams. In order to do that, in order to convert between moles and grams or grams and moles, we had to use something called the formula mass, right? In order to do that, we had to go to the periodic table and add up all the different elements and their masses and multiply any of the subscripts necessary, right? And then that got us our formula mass. Once we had our formula mass, it was only always 1 mole divided by formula mass or formula mass divided by 1 mole, right? And those are the conversion factors, right? Those fractions we used in order to convert between moles and grams. And the last thing we talked about was liters, right? Liters or volume of gas. And in order to do that, in order to convert between moles and liters, we had to use this special number here, which was 22.4 liters, right? And that was an easier one, right? Because all you had to do was 1 mole divided by 22.4 liters or 22.4 liters divided by 1 mole and use one of those two conversion factors to go between moles and liters. Now, this whole mole map here is really important because not only does it show us that we have to use this number for molecules, formula mass for gas, or formula mass for grams, and then this number 22.4 liters for liters in volume, but it shows us that everything has to go through moles. If you guys planned on, let's say for example, some question gave you some amount of liters of gas, right? Let's say it gave you 45.2 liters, and it wanted you to convert that into some amount of grams. Okay, well, you couldn't just take any old number and say, hey, 45.2 liters is going to instantly go from liters all the way over to grams, right? You can't just do that. You have to stop at moles first, right? So this is almost like a flow chart. If you start at one of these 4 locations, you always have to go through moles in order to get there. So in order to convert this 45.2 liters of something, it's got to go from 45.2 liters into some amount of moles first. Okay, some amount of moles. And then once we go from moles and we have some amount of moles, we can convert from moles using formula mass. I'm just going to abbreviate this FM then from formula mass, we can convert from formula mass into some amount of grams, right? So this is almost like a flow chart showing that, like, hey, every time you have to convert between any of these units, you always have to go through moles first. Worst case, when in doubt, just convert into moles and go from there. In a couple of different easy ways to start out by doing that is using something called the mole ratio. All right, the mole ratio is a little bit difficult to kind of pick up on right away. And it comes from all of our different chemical reactions, and more specifically, our balanced chemical reactions. These balanced chemical reactions show the mole ratio between the different reactants and products. So, for example, we've got this balanced chemical equation here, and how you would phrase this. And take careful note, guys, at all the coefficients in front of these formulas here, right? There's a 2 in front of the K, nothing or an invisible 1 in front of the BR, 2, and then a 2 in front of the KBR. How you would phrase this is actually, these coefficients, guys, are not just called coefficients. They're actually some amount of moles. And obviously, we talked about coefficients back in Chapter 7. Then Chapter 7 turned into talking about stuff from Chapter 8 here. Or, sorry, Chapter 6, which is all the mole stuff. So I didn't have the opportunity to tell you that these coefficients are actually just the amount of moles of that particular formula, right? So we've got 2 moles of potassium. Well, that comes from the 2 moles of potassium. Let's grab a different color here. Right, so this 2 here tells us we've got 2 moles. This invisible 1 here, right, this is an invisible 1. This invisible 1 tells us we've got 1 mole of Br. This 2 here tells us we've got 2 moles of KBr. So again, these coefficients in front of these formulas here tell us exactly how many moles of that substance we have, all right? So it's all based on, again, moles. Everything connects back to moles. Now, when you've got these comparative amount of moles here in these balanced chemical reactions, you can write, yes, unit equalities. And I'm sure you guys are all very, very happy to see unit equalities are still alive and well. But again, yes, mole ratios, all this stuff have a lot to do with unit equalities. So they're back in action here. Now, if I wanted to compare any of these amount of moles of something, I could say that, you know what, this right here, this 2 moles of K or 2 moles of potassium are equal to, well, this 1 mole of bromine gas, right? Br, or bromine liquid, Br2. And I can represent that by showing this in terms of a unit equality, right? 2K or 2 potassium equals 2 moles of potassium equals 1 mole of Br2. Now, if I wanted to compare something else, I could say, well, let's say if we can compare potassium to potassium bromide, KBr. I can say that, hey, 2 moles of potassium equals 2 moles of KBr, or 2 moles of potassium bromide. The only thing left to compare here is the bromine, the liquid bromine, Br2, and KBr, and I can represent that in a unit equality by saying that 1 mole of bromine liquid equals 2 moles of KBr, 2 moles of potassium bromide. So again, we're kind of taking exactly what we have here, right? So if I were to pinpoint this, I could say, hey, I've got this guy right here, appearing right here, and appearing right here. This 1 mole of bromine is appearing right here, and also appearing right here. This 2 moles of KBr is appearing right here, and also appearing right here. Okay, so they're coming directly from the actual balanced chemical equation itself, right? Nothing crazy here going on. We're just taking things directly from the balanced chemical equations here, and creating these unit equalities I keep telling you about, right? Again, very familiar with unit equalities, hopefully. We've talked about them a lot this chapter. They're still back here in this chapter 8 here. Now, again, if we have unit equalities, hopefully you all are able to pick up on this now. If you ever setting 2 different measurements equal to each other to create a unit equality, there are 2 things you can create from your 1 unit equality. And yes, they are our conversion factors. So if I have this unit equality here of 2K equaling 1Br2, that's going to give us our 2 fractions, 2K over 1Br2 and 1Br2 over 2K. And again, as soon as you get the 1 fraction, you can flip it to get the other fraction. And again, just to make sure we're on the same page here, 2k divided by 1br2, this is the same thing as this guy. And then in order to get the proper second thing, you basically switch sides here, right? The 2k goes on the bottom and the 1br goes on top to create this guy right here, okay? So again, we should hopefully all be relatively familiar with conversion factors and how to create the two fractions, right? Those two conversion factors from one unit equality. Let's try the second one here. 2k equals 2kbr. Make a fraction out of them, right? 2k divided by 2kbr, and then you flip it to get 2kbr on top and 2k on the bottom. The second one, or the third and last one here is 1br2 equals 2kbr. This is another unit equality. Well, again, one unit equality can always turn into two conversion factors. So divide 1br2 divided by 2kbr, and then you flip it to get 2kbr on top and 1br2 on the bottom. So again, nothing really new here, just kind of different in terms of what we're working with. Once we have our conversion factors, once we have our two conversion factors, guys, just use dimensional analysis, right? It's the same thing we've been doing for a little while now, these last couple of weeks. Let's get some practice here doing just conversion factors here for mole reactions or mole ratios. So the question reads, write mole ratios for the following reaction. You've got this reaction here, which is 4 aluminum solid plus 3 moles of oxygen gas equals 2 moles of Al2O3, which is aluminum oxide. Again, all we're doing, guys, is we're taking these things here, 4Al, 3O2, and 2Al2O3. And we are creating fractions out of them, right? We're setting things equal to each other and creating those unit equalities, and then the one unit equality turns into the two conversion factors. All right, so if we set things equal to each other, we're going to create this here, and this here. And how we got that, we're going to work backwards here a little bit, is this. Okay, we set 4 aluminum equal to 3O2, right? So 4Al equals 3O2. Well, you've got this unit equality of 4 moles of aluminum equaling 3 moles of O2. Well, make a fraction out of it, okay? Divide this by 3O2 and divide this by 4Al. And you've got this guy right here equaling this guy right here, and this guy right here equaling this guy right here, right? And it's the same thing for the other ones here. All right, this time around we're comparing aluminum and aluminum oxide. This time we're comparing oxygen and aluminum oxide. Okay, so nothing really crazy, nothing different here that we've been dealing with. It's just that these are where the fractions are coming from here. So these are our mole ratios, right? Our mole ratios are the unit unit equalities turning into the two conversion factors. Now the next one here, mole stoichiometry. What if they don't give us the proper amount of moles, right? So we've got the exact same equation here, aluminum, oxygen, and aluminum oxide, same amount of moles, 4, 3, and 2. But they gave us a different amount of moles here, right? They initially told us, well, we've got 6 moles of oxygen here, and they want us to convert that into some amount of moles of aluminum. So we've circled our 6 moles of oxygen. We are looking for some amount of moles of aluminum. So that means we're working with aluminum and we are working with oxygen. That's it. We're just working with the 4Al and the 3O2. We are not working with this Al2O3, this aluminum oxide at all. So we can kind of just cross this out to a degree. Now, since we're working with these two things here, we set them equal to each other. 4Al, oopsie, it's supposed to be lowercase. 4Al equals 3O2. Now create your conversion factors from them, right? Divide it by each other. So 3O2 divided by 4Al, right? And these are our two conversion factors here. We're trying to convert 6 moles of oxygen here, right? So that's our starting number, 6 moles of O2. We have to multiply this guy by one of these two fractions here, right? But again, it's oxygen up top here. That means oxygen has to be in the denominator of one of these two fractions. The only one that has oxygen in the denominator here is this guy right here. So we put this in here. 4Al divided by 3O2. Close the parenthesis. Oxygen cancels with oxygen. We are left with aluminum as our unit here, which is going to make sense for us because we put a box around aluminum, and we are good to go. Exit the drawing, and this is the full thing, right? 8 moles of aluminum is what we end up with here, guys. Here's the next couple examples. Pause where you need it. Pause where you need it.